Today's farmers face uprising challenges in a global market. The shortage of skilled farm workers, the prohibition of chemicals, and electrification of agricultural machinery present future challenges. Thus, ETHAROP aims to decrease monotonous and physical demanding fieldwork by automation and integrated digitization.
Localization is essential for a mobile robot. The robot needs its global but as well as local pose. The global pose of a field robot can be easily determined via GNSS.
A global GNSS-based localization strategy can be improved by adding local features, such as odometry and IMU data or plant pattern recognition. Most of today's field applications can be realized using a reactive path follower and a robust multi-data localization strategy. The omnidirectional kinematic of the ETHAROP simplifies the path following process. It decreases turning areas and allows quick drive mode changes. In the future scope, autonomous path planning will become a bigger part in agriculture robotics. Intelligent field robots will increase uptimes by actively avoiding collisions via bypassing. The autonomous approach to service points enables automatic tool change or refilling of working supplies.
ETHAROP is designed in a modular way to satisfy research demands as well as intense field trials with local farmers. Like many other mobile systems, it consists of a battery to buffer power combined with a range extender. The other side hosts a control cabinet, communication systems and some sensors. To combine different production processes, like for example fertilizing and weed control, ETHAROP features 2 tool slots in this configuration.
One challenging and interesting application is a selective weeding system. Here, a high voltage electrical shock is applied to the weed in order to destroy the biological tissue.
The advantage of a selective weeding approach without chemicals is quite obvious. The discussion of a glyphosate-free cultivation of crop plants in Germany motivated us to develop the following system based on machine learning algorithms combined with standard image processing techniques to identify and localize cultivated plants.
Methods based on deep learning have proven to be robust and precise in classification and segmentation of crop and weed plants. One major factor closely related to the model performance is the quality and quantity of the training dataset. Traditionally, the generation of a dataset for object detection is time-consuming and costly.
Therefore, we enlarged our dataset with photorealistic synthetic subsegments. We make use of highly detailed 3D models of crop and weed plants. By mutating the properties of these 3D models, we can generate a diverse and large dataset for all plant models.
This approach enables ETAS, our field robot software, to adapt to different domains like day and night, rain and sun,